we will see how it goes.
Yes.
And I propose also to reposition camera from the beginning that we will notice in the just a little bit right. Yeah.
Okay, you see, I will do the following. I'll move the of course I'm not repositioning camera, okay. And I also need to switch this off.
I think it's
Okay.
possible a little bit more, right?
Okay.
No, this is the opposite direction. One more. No, more, little bit. Now it's okay. Yeah. No.
Okay.
No, once again. Now it's okay. Yeah. Great.
Okay. So, so I'll try to comment on several things. First thing would be relation. I would not say relation. I would say towards relation to reduction of KP. Second, I will comment on TODA. But before I'll do 1 and 2, I'd like to discuss the point number 3. And this point number 3 is the higher residue pairing. Because without higher residue pairing, it would not be clear. I mean, the formula that I'll write. So in order to write formulas and in order to understand things, we need to see the higher residue pairing. So once again, this higher residue pairing is needed to prove something. And point B, to write down formulas. In particular, if we'd like to have some kind of relation, we need the theory with cyclicity, okay? And point C, it is needed as a lemma to be used in where? In other string theories. Okay, in other places in string theory. So this trick that I'll use here was used in order to regularize Feynman diagrams, Feynman divergences, and also in ambidextrous strings. So this trick has many applications. That's why it is called localization trick. And I decided that it is good to discuss it in some detail, okay? So before I start to discuss something, first I like to record myself. 1 second. So I do not have a right to record. Sam, could you give me the right to record? Sam, Could you give me the right to record? Okay, thank you. So maybe that's why, you know, I'll start with point number 3, and then I come to the point number 1, because I will try to write down some explicit formulas here, okay? Actually, because when you say construction like this, construction like that, it's not convincing, you see? You cannot, it is hard to convince people by constructions. It is much more effective if you convince people by writing down explicit and surprising formulas. Okay? So after I'll describe this, I will write here an explicit formula for the 4-point function. And you will see the things mysteriously work. Okay? You see, now I realized what would be the proper plan. So you see, I start with 3, then I go to 1, and then I'll go to 2. Okay? Okay? So this will be my plan. So I am sorry for changing plans, but now I realize that it's the only way to understand. So what we discussed yesterday. Yesterday we discussed the pencil of cohomology. It was Q1 plus ZQ2 cohomology. And we understood this pencil as a Q plus Z G naught minus. And I presented argument why this Z corresponds to first Chern class of the line bundle. So yesterday I explained how to construct the differential form, and how in this construction of differential form, this Z that appears here brings C1. And now I would like to do the following. Now I'd like to find the pairing on QZ cohomology. So what I'll explain here probably works in general context. So I will not try to do it in the maximal generality, but I'll do my best to explain what is going on. So suppose I have X, non-compact, manifold, and on this non-compact manifold, I have superpotential. And also generalized complex structure. That I'll write like D bar plus DW. DW1. And now on So I need to say, so it's Gorin, I think. Okay. So
Yes,
now
hello.
I'd like to write down the pairing on this cohomology. So first, before I write the pairing, let me ask the first question. What is the space? On which I study this QZ cohomology. So since the space is non-compact, I have many choices. So having this many choices, I would study the space. So there are two spaces. Okay. So first space would be so-called Schwarz space. Schwarz space. Now, when I say Schwarz, I do not mean John Schwarz. When I say Schwarz, I do not even mean Albert Schwarz. When I say Schwarz, I mean Laurent Schwarz. Okay, many Schwarzes. I think Laurent Schwarz. So it means that you have infinity and infinity. You have non-compact direction. And the differential form goes to zero very fast in this direction. So you may ask, what does it mean to go very fast? So suppose that we have this x. We may include it into compact space, compactification, the compact space. And let us assume that x is this thing minus divisor. Okay? So let me work in this setting. And this divisor has an equation. Something like f equal to 0, at least locally. So what could be the Schwarz space here? So the Schwarz space would mean that the differential form goes, what does it mean to decrease very fast? It means that it goes like, approximately, like something that is exponentially, something like this, for some alpha. So actually it means that if you take any pole and you multiply by omega, you can take integral. Integral converges. Okay? So I copy this definition from, you see, from the notion of infinity in C. Okay? Origin of definition. Suppose we have something like 1 minus x squared. So it's clear that, and I would like to consider something that are polynomials and x1 and x and x bar. So when I say Schwartz space, I mean something like this. With some alpha here. On CM. Actually. So infinity is solution of equation. Infinity. So here C is included in CP1, right? Equation, so divisor, that is infinity, is 1 over x. So what does it mean to write down this term? It actually means that, so function for infinity is 1 over x. So when you are writing down this exponential guy, it means that you work with something like 1 over. And I think that it's a proper generalization. Okay? And this alpha could be small, but non-vanishing. So it's the idea. You may ask, why I'm doing all this? Why I am not satisfied with the standard definition of square integrable forms on CEM? It's because the space where you can apply this theory is much bigger. It's not only for polynomials. It is basically for any manifolds. And the fact that it's like this for any manifolds showed up in Ambi-Twister string, in Krichy-Wehr model, in regularization of Feynman integrals. Okay? So before I will proceed, I'll give you motivation why this is needed. Okay? Why should I do this while Kyoji Saito was not doing this? Okay? It's because there are many divergent integrals. Okay, so let me make an introduction about divergent integrals. Okay? And I think I could recommend lectures of Misera at Princeton on this subject. But I will explain it my way, okay? And also, Shi Li has similar ideas. So I can only say that I had these ideas in 1993, okay? And they are published in my paper on 1998, I think. Last century, okay? So these are ideas of last century. Consider configuration space. So here we have points. So for me, it will be point on Cn. And then consider the correlator. And when we study correlator, it's a function of points. Now, so I write coordinate x. Now, sometimes we do not need to study the correlator itself. Sometimes we study integrated correlator. We would like to take this, we would like to take an integral. I'll write it dx. So when are we doing this? When are we integrating something? This happens if we study the formation of the theory. So we have something like functional integral over, okay, points on x, not Cn, point on x. Here we have Lagrangian plus perturbation. So it is the basic story of the functional integral. And I say that I would like to consider things perturbatively in T. Perturbatively in T. So that's what I'd like to study. Okay, I'll write it like this. N times. And here I have, okay, 1 over n factorial. And it's here when I say that, so I need to study this integral. The main issue in quantum field theory is that this integral is divergent. You may ask how it is divergent. In order to understand how this integral is divergent, you can do two things. First thing is that I will not go this way. But one of the ways to understand that this integral is divergent is to decompose, fields phi. Take Fourier series on X, make this computation and see ultraviolet divergences. So it is this way to see that it's divergent. However, I would like to take another approach to see why this integral is divergent. I would like to say that here we have integral over configuration space on X, because I have actually n points, and I have the correlator of delta Lagrangian at point x1, delta Lagrangian at point xn. Okay? So I'll ask Dong. So since you are a mathematician, is it clear what I'm writing here? How does it feel? How does it fit your mathematical intuition? That I'm studying the would-be functional integral, I decompose. So is it okay with you that I decompose things like this?
For me, it's okay, except that if you want to replace the nth copy of X to the configuration spaces, usually we blow up the diagonal part. So
exactly. Because here, when I say configuration space, I would see non-compactified.
Okay, good.
So it means that it is configuration space here is not compactified. So it is x to the power n minus diagonals delta. Is it good to write it for diagonals? Okay, and then later, when I will try to deal with this integral, I may think how to compactify. Okay? But before I compactify, I do things like this. This is already a regularization, cutting out diagonals. Because actually, there was no configuration space here. I was expected, okay, due to definition of functional integral, I had to take integral over x to the n. But here I change the definition, okay? So I would like to say that cutting out diagonal is a change of definition, okay? So what can we say about this object in general? So this object is, first, it's kind of it has singularity on diagonals. So how can we see that this object is in general has singularity on diagonals? By examples. Example 1. Assume that L is quadratic. Here I need to make a comment. What do I mean that some function, not like that integral is quadratic? What do I mean when I say that function is quadratic? I mean that I assume, okay, I assume that there is a linear structure, i.e., there is a linear structure, actually a phi, structure on phi, and then the action being a function could be decomposed into powers, okay? So after I take this linear structure, it is correct to say that something is quadratic, right? Then I may speak about quadratic. You see, I say that it is an example because this would be generalized. I presented it in such a way that you will see that it is just an example and not the general case. So, if it is quadratic, we know the structure of this guy. So, delta L is expected to be local functions of phi and its derivatives. So delta L are expected to be polynomials. You may ask what happens if they are not polynomials. And here I unfortunately have two cases. Case 1a, polynomials. Case 1b, stronger. So among examples in point 1b, I say exponentials. Okay? And we will consider these cases one after another. So if I have polynomials, yes, for case 1a, if they are polynomials, I know that this correlator is the product of the green functions and maybe some derivatives, d to the power k. Okay? So what is the green function? Green function is a green function of the elliptic operator. And you may check that green function goes like to some integer power. How should I write integer power? N. Okay. So it goes like this. Actually, yes. So sometimes in the massive theory, there could be exponential. Okay? There could be exponential. But when I consider x1 going to x2, so it's the region, I may ignore this. So it is short distance behavior. When x1 goes to x2, green function goes like this. So derivatives of green function go like this. Okay? And there is a particular case where green function is what? Sometimes you can have n equals 0. So n equals 0 actually means, you know that x to the power 0, do you know how are we calling this function? X to the power 0. It's log.
Log. Okay.
Okay, or actually polylog. So it is, I put this in quotation marks. Okay, so log is something that you have when the power is 0. you don't have 1. You have something more interesting.
I was kind of expecting because green functions sometimes have a log.
Of course. You see, when I say that x to the power 0 is log, how to say? It's a slang. You see, it's a principle.
I will consider it as integral of 1 over x, so it's fine for me.
Yes, exactly. Of course.
Anyway, I got what you mean. Yeah.
Okay, you got what I mean. It was my desire that you got what I mean. Okay, so you see what's going on. So we know the singularities. Okay. There are these singularities. Okay. And then we are trying to integrate over this space. And you know what? This integral diverges. Okay? So the type of the divergence is, so you may, it's a question how you call it. It depends what is the coordinate in which you treat this divergence. Still you have divergence. So and it is these divergences that started all this issue of that quantum field theory is not well defined without renormalization. So these are actually Feynman diagrams. Because of these poles. Moreover, it is clear that the degree of this pole is related to the dimension of space X. Okay? So basically, it's because you have, so green function satisfies this equation. So what you have here is basically for scalar fields, x1 minus x2, and here we have dimension of the space X minus 2. So it means that you don't have problems for scalar fields in dimension 2, but then you will have problems with derivatives, because when you take derivative, you increase the pole. So in general, you have this divergence. So the question is what to do. You see, it seems that I'm actually describing you what is called ambitwister approach or regularization approach, but idea. So one of the ideas is to regularize, but how to give meaning to what are we doing? So it is better to have here cohomological meaning. Okay. So let us assume that green function is analytic, real analytic. On where? So green function is of course a function on x times x. All right. So it is a good assumption. So in examples that we have, it is real analytic. I don't know how we can prove it, but in examples that I know it is real analytic, and I don't see the place why it should not be real analytic. So when I say assume, I say that if x is like r, so typically green function is something like either exponential of something x1 minus x2, some mu x1 minus x2 modulation. So say it's for I don't remember, for R3 or R4, just something like this. So for when x is R2, you have the Bessel function. You cannot write it in such a nice way, but it's definitely analytic, okay? So I assume this. I don't know the proof. It's good for me to know the proof. Maybe I should know the proof, but okay, I consider it as a technical mathematical equation to prove that the Green's function of the Laplacian is real analytic. I don't know how to prove. Okay, so if it is real analytic, then I would like to reconsider the integral. So it is this, so I have this integral, and here I have something like dn x bar. I would, so, and I integrate this over x to the power n. I would like to understand it as follows. I would like to analytically continue this integral. Or at least not analytically continue. I would like to, sorry. I would like to consider, not analytical continue, I'm sorry. I'd like to consider cohomological interpretation of this integral. And here I refer to lectures of Mizera. I think with Z, I always, okay, you know, I'm better at it, right here, at Princeton. So he gave lectures under the supervision of Arkan Hamed. And he also wrote a thesis. And he is a rising star. So it's good to hear him. He also wrote a lot of papers. So he said, look, at the moment we think that that X is complex, manifold. So we may try to consider this as a integral over the fundamental class, okay? And we would like to do it in a cohomological fashion, okay? I mean, to consider these integrals. So we would like to see the following thing. We would like to interpret what is going on as a result of the integration of differential form. And here we would like to cut out diagonals. Then we would like to study what? We would like to study proper cohomologies of omega, deform it in cohomologies, and give another meaning to this integral. So this is kind of an idea. What to do? That's how I'm coming to this notion of considering such integrals with polynomially divergence omegas. So trying to give meaning to it. And what is interesting is that such integrals appear already in type B models, okay? So this is the fundamental problem. This is the problem of divergences in quantum field theory. But it also appears in I say that it appears in type B model. Okay, I said it was example 1. However, there is example 2. I cannot have, so if I number example, I cannot label it by, if there is 1, there should be 2, right? Where you replace delta X as a so-called operator in, say, conformal field theory. Then you have OPE. And then the same singularity. And you want to give a meaning to both divergent and convergent integrals, okay? You need some tool to deal with it, okay? Okay, example 1, example 2. So to be more specific, in example 2, you may consider, say, WZW model, like WZW model, like delta L is replaced by something like current bilinears, and you have divergences like this and higher terms. So it's example. I put here WZW because the idea is that you are not treating WZW in terms of free fields. Come on, what kind of free fields? It's a Lie group. However, you have currents, and you can write almost everything in terms of currents. There are also representations of the algebra integrable, and you can also write down similar things. You see, once again, I want to be constructive. You see the same type of divergence. And there are other examples. Okay. Since it's my talk, okay, I have a right to put example number 3. Because I like it. So already in WZW it's okay. However, in example number 3, I can consider the instantonic sigma model, where instead of currents, you have differentiations of the target. Okay. So this is called chiral algebras. The difference is that I consider both holomorphic and anti-holomorphic. And then as delta L, I consider something like differentiation of y times differentiation of y bar, and have structure similar to WZW. And in this way, I can find that the divergences are related to Ricci tensor. So this thing is considered as a inverse metric, and these divergences would lead to Ricci tensor. And it is my paper with, okay, Losev, Kyle, Marshakov, Zeitler. So we have these examples with L being quadratic, and in general case, we have these divergences. And that's why, in particular, Shiley is studying exactly these integrals and these divergences. So everybody are doing that.
Could you explain a little bit more how this Ricci tensor related to the divergence of the integrals?
Yeah. Okay. Okay. So it is
very precise. I just want to get some idea.
Yeah, exactly. So okay. Suppose we have, well, let me make a statement. Manifold Y. Then I have the space of differentiations of Y. In the smooth case, there are vector fields. So if Y is complex, I may consider V's that are smooth sections of T10. Okay, smooth. However, Okay, then I have the object that is 1, 1 by vector on Y. So it belongs to the smooth section.
So it's an inverse of certain Hermitian metric.
Yes. So if it is invertible, it corresponds to Hermitian metric. If it's not invertible, it's a something. Now, I'd like to understand Gij that belongs to the completion. So what I do? I'd like to study something like beta function. So I take Y. I cut out some divisor, very different divisor, not divisor of this type, such that I would like to understand Gij on Y minus D as an element of, now I say holomorphic differentiations of Y, anti-holomorphic differentials of I tilde. What do I mean by this? I mean, what I keep in mind, just consider something like CP1. So the number of differentiations of CP1, holomorphic differentiations, and here there was smooth, is finite dimensional, right? Like 3-dimensional here, 3-dimensional here. So I can actually make, have only finitely many interesting bivectors. However, if I cut out divisor D, I can get, for example, C. And I can study, and then I have a lot of differentiation. And so I'd like to say that Gij bar belongs to this tensor product over C. And these are, of course, holomorphic. So it's anti-holomorphic. So actually, what I mean, that the smooth bivector could be decomposed as Z to the K, Z bar to the L. Okay. Sum over K and L. So I consider analytic. Okay. So I consider real analytic. So real analytic on the open set could be decomposed in this way. Okay. Now, let me call, you see, I have too many D's. V belong to this. Then there is observable O of V. And it goes like this. O of V1, V2, commutative. So this is the chiral algebra. It's called supersymmetric case. There is also pure bosonic case, but I consider this. Now, Now, as delta L, I may consider what? O of V bar, okay? Let me put here indices and let me sum. So it's an element of a tensor product. Here I take out the divisor. So it means that I actually need to consider some sheaf version of it, okay? Sheafization. So this is kind of the risky open set. Then delta L of Z, delta L of W goes as follows. Moduli square. And here I have an interesting object. Here I have delta L of what I call double bracket. So what is a double bracket? Double bracket means actually that I have VA bar VB and I have a sum, okay, and that's what that's what stands here, and then I understand this as an element of the same space of diff times diff. So this is this double bracket operation. So I decompose into pieces, I take commutator and I consider it here. So actually it means that when I'm writing delta L of this type, I consider on the space diff times diff, there is a double bracket structure. So you decompose as a product and you take bracket in each of arguments and that's it. So this is how it's written in the basis, and this is the general thing. So what I have here, once again, I have something that is of the type 1, 1, okay? So this is something of the type 1, 1. And surprise, surprise, is that for Kähler, GIG bar, it is Ricci tensor. Now, if it is not Kähler, for non-Kähler, it is actually Ricci. No, Ricci minus something like this. I'll call it T. So what this T is, I need to take GIG bar. I'm making out of it this guy. So this is, and then I consider this as a 114. Oh, sorry, IH. Okay, I'll write it DB. that I'll call B. And then I can consider this as a Kalb-Ramond form. Then I can write an energy momentum tensor. It has this form. It goes through the curvature of B. And that's it. So I have this formula. And these are nothing but the bosonic string gravity equation, this one. And here is a double bracket. And I published it like 14 years ago in the paper with Marshakov and Zeitlin. Maybe we published the particular case, but it was clear that this term would come out. And from this consideration, at least I proposed, okay, without them, that you can write bosonic string gravity for schemes. Because for schemes, you have this. So right-hand side is defined in many cases. Left-hand side is only for the smooth manifolds. So this is the proper definition for bosonic string gravity, and it should work in the context of algebraic geometry. So you can play with zero-dimensional schemes, with any schemes. So this is bosonic string gravity for schemes. So I didn't want to tell you, Doc, this, but you somehow asked me questions and questions, and according to the rule of our game, I'm answering your questions, right?
Okay. It's good to know some more stories around there. So you're saying that you allow some poles at the chosen divisor of the Galen manifolds?
Okay, so you mean where? In this story?
Yes, in that.
Yes, of course. So I understand that so-called beta function or something should be local, okay? So if it should be local, I can localize in the risky way, okay?
And if I want to understand the relation on the bottom of the board as the operator product expansion, then
of course. So it is. So this is operator product expansion that people are writing in the chiral algebra theory. By the way, you were interested in chiral algebras.
Yes, and the coefficients of this singularity gives you a Ricci tensor.
Yes.
Certain forms. Okay.
Yes.
That's
Ricci, not only Ricci tensor, Ricci tensor modified by so-called stress tensor of the B field. So it's not a coincidence. It's just exactly the bosonic gravity. And it is, and it comes from the computation of beta function in instantonic theory that we developed with Nekrasov and Frenkel. You take this theory, you deform it from the instantonic point, and you check what the beta function should be. So you see that it is like this. It is given by the double bracket formula. And you see the notion of double bracket was put, you see, double bracket, by Zeitlin. And I was so jealous that, you see, we had all formulas, but he said, look, it's just double bracket on differentiate. So I was not quoting him for several years, but now I need to apologize. Yes, the interpretation of Ricci as a double bracket was due to Zeitlin. We had all formulas, but Zeitlin said, look, it's a double bracket. So it's Zeitlin.
Okay.
Okay, so I apologize. Yes, I use this double bracket without referring to Zeitlin. Now after many years, I apologize. You see, jealous. You see, it's very natural. You see, So after I have all formulas, just come and see, look, okay. Oh, it's not too late to apologize, yes, it's. Okay. So this is. So I gave this example to show that these divergences are quite natural. But I gave you example 1. I gave you example 2. But now we need to see the example 3, okay? And I will give you example 3 because the example 3 is also very relevant. And I actually wanted you to, I actually want you to see all examples all together, okay? Example 3. And this example 3 is related to so-called ambitwisters. So remember that I said that delta L is a vertex operator. So now, one may ask, when I say vertex operators, why I'm not studying the vertex operators of bosonic strings? Okay? So once again, example 1, I studied something like this. Example 2, I studied something like this, approximately. So here are just vector fields. So in example 3, and these are like polynomials, okay? And here I study exponentials, okay? Now, in example 3, the OPE of e to the a chi phi 1, e to the, sorry, chi 1. So we know what's going on. I have this type of divergence. So you may ask, what is the difference? What is the difference here? Why this is different from this? Why 3 is different from 1? Why 3 is different from 2? And I need to tell you why it's different. It is because here we have real number. And do you know how people are calling these numbers, k1 times k2? In string theory, they are called Mandelstam variables. Have you heard this? So at some moment you will look at ambitwister strings and so, and I just need to tell you how people think about it. People are thinking about particles, about scattering of particles. So you understand this diagram. So these K's are momenta of particles in Minkowski space. However, you may consider different spaces. So there is a conservation of momenta. So here we have K1 plus K2. Now, there is so-called on-shell condition. On-shell condition means that K1 square equals to mass square. You may ask, what does this mean? So if mass is 0, it means that you have a light vector, okay? So this is the main equation of our world, that we are actually waves, and this equation is called the Klein-Gordon equation. Maybe you heard about it. So this is Klein-Gordon quadric. Okay. With minus here. Okay. So this is a Klein-Gordon quadric. By the way, do you know what Dirac did? In the language of modern algebraic geometry, Dirac found
the square root of that operator.
It's not, you see, it's how physicists say about it. But we are kind of mathematicians. At least we pretend to be. We may say that he found non-commutative points on the Klein-Gordon quadric. It's interesting. By the way, I never heard that people reinterpret what Dirac did in modern language, in the language of modern, last century algebraic geometry. So Dirac just studied metric solutions, right? So he wrote an ansatz. So Dirac. So what does it mean? Solving equations in terms of matrices. So it's a problem that people study in algebraic geometry, right? Non-commutative points. Okay? Why nobody is saying this? I don't know. So Dirac is great. Not only he did this, people now are not just explaining what he done, okay? So he said that solutions to this quadric could be obtained from solutions to linear equations. So, okay? So what people were doing in 60s and 70s, I just don't know. Not reading other people's books, not trying to understand things. Okay. Nevertheless, so here is this Klein-Gordon quadric. Let us assume that we have a mass quadric. Now, what is K1 plus K? So now, let us see. If this belongs to the quadric, and if K1 is on the quadric, and K2 is on the quadric, would K1 plus K2 be on this quadric? I'm sorry, you see here I have different indices. So one mu, so it is mu here. And this is, you see, with these vectors mu. So here one is the number of the particle. So let us compute K1 plus K2 squared. It is K1 squared plus K2 squared plus 2K1 K2. So this is 0 because it comes from the quadric. And this is not on the quadrics. Okay? So K1, K2 is something that says how far you are from the quadric. And there was a man called Mandelstam who just classified this. So how people interpret this mismatch? They interpret this mismatch in the following. Suppose you have to the system where these two particles have zero space momentum, okay? Or just hit and sit. Then this mismatch is the square of the energy that you have, having zero space momentum. And this is called Mandelstam variable S. So I gave you the meaning. You know, in Geneva, proton, antiproton, bam, no space momenta, however, a lot of energy. And this energy is this S. And it's exactly what stands here. Okay? And this thing could be real. There is no quantization of energy in the world if it's an energy. In order to quantize energy, you need to say that time is periodic, and that's very unnatural. So it is real. Real and not integer. And this is a difference. So we can have singularities of the polynomial type, and we can also can have this. So singularities where we have branches. So if we analytically continue here, we have kind of the branching phenomenon. Okay? And we exactly have this branching phenomena when we do these vertex operators. However, it is these vertex operators and this branching phenomena. So it happens in bosonic string. And then you say, okay, here is the energy. How can I take difference of coordinates and the power of energy? Okay? I can take it only to some power that is a number. It could not be measured in what? In joules. You see, I cannot take difference of points and put it to joules, to the square of joules. That's why here is the string mass squared. So so what is this number? You consider the energy of collision in joules. You have string mass. You divide one over another. You have a number, real number. And this is this divergence. So that's how these divergences look like. Oh, singularities. This is singularity on the device. By the way, I think now, I see you're a bit tired. We need to make a break. So would we have Pashamyov? I asked him to be a time policeman. So after you see this problem of taking integrals of the configuration space, and you see different type of divergences here, you understand that this is not a crazy problem in mathematics. How to integrate divergent form. You may see that it is a fundamental problem in mathematical physics. So that's what was realized by Mizera and also by Shili. And that's what people somehow missed. So the question would be how to give meaning to these integrals. And and very particular case of this would be QG side or higher residue pairing. And QG side would never know that what he was doing is related to the to the equation how to define proton anti-proton scattering of hadronic collider. Okay, he was doing periods of integrals. So it is in the same scope of mathematics. So it's interesting. Okay, I'll discuss it after the break. Okay.
So I think it's good to have a 10 minutes break. So we resume at like 35.
Ah, good. 10 minutes break. Yes. I would put my alarm. Yes, I see. 10 minutes break, good.
Okay. Andrea, I think you should turn on your mic. Your device is muted. We can't hear you.
Yes. So mic turned off because of several minutes of non-interaction. So it's a robot that did it. So what I have explained to you was 3 examples of divergent integrals in mathematical physics. However, there is the example number 4. And this example number 4 comes from the singularity theory. Example number 4. Suppose you have cohomology like this. The easiest way to find this cohomology is to first to consider cohomology of d-bar and say that, good, we are studying everything holomorphic. Forget d-bar. So then we study cohomology of this. And it's very easy to study cohomology of this. Top forms. Okay, holomorphic top forms are closed. Because I multiply by dw, I just, so they are killed, holomorphic top forms. So since space is non-compact, I can have many holomorphic top forms, right?
Mm-hmm.
So since I'm working here, I have top forms of the form like holomorphic function. And here I can have a poles. Okay? Of the various order. Okay. When f is the function for the divisor, right? I can have a lot. So this corresponds to polynomial of x dx. So that's how I write it in an invariant way, and that's how I write it in an example CP1 minus infinity. Okay. So general case example. Now, what I want to do. I would like to study the pairing, okay? Pairing on dw cohomology. So, and actually I would like to study even pairing on dw plus zd cohomology. So how would I work in the compact Kähler case? In the compact Kähler case, I had d bar plus zd, okay? I just say cohomology are forms on the compact space, harmonic forms. I can just multiply them and integrate. Multiply and integrate. But it is wrong. You can define such multiplication and integration operation, and it would work. It would actually work in the compact Kähler case, but it is wrong in general. Let me try to explain to you why this multiplication and integration is wrong in general. Okay? It is absolutely not obvious that it is not the proper operation. You see that it is not proper operation only after you study generalized complex structure. It is because you want to have a pairing that descends to cohomology. Of course. You want to have cohomological pairing, okay? And the tricky thing is that when you have d bar plus dw, okay? So let us see what goes wrong in the compact case. Sorry, what goes wrong here? Why wedge is not a proper pairing? It's because when you differentiate by parts, this goes to d bar minus. So here we have minus, here we have plus. So in some sense, cohomology of W are paired with the cohomology of minus W. And it's not what you are going to have. Okay? But there is a way to go around. And it is called while operator. Okay? If you modify it by the complex number I to the power P minus Q, where P and Q is the type of the form, when you take this thing around, you will cancel this minus sign. Okay? Okay? In this case, you will get cohomology on pairing on cohomology of Q. Is it clear? However, when you consider the pencil plus ZD, when you go all the way around, you will get minus ZD. Here is the minus side. It's interesting. So here is the minus side. So actually, this pairing wouldn't be defined, would be a pairing between cohomologies with index Z and cohomologies with Z with minus Z. Okay? And by the way, it's exactly what you can see in Kyrgyzaitis paper. Okay? You may ask, why this Z minus Z comes out? This is the reason. Hmm? When I first wrote about this pairing, I missed this I. And I had a sleepless night before my talk in Trieste, when I found that something is wrong. And I had to find this I during the night before my talk. And I was a bit stressed. But during that night, I got it. So it was a nice sleepless night. That's why I remember this. So that's why maybe in some early papers I don't have it. And but I think it should go like this. And this explains Z to minus Z. Still, just assume that I'm making this pairing. I need to take a pairing between two holomorphic top forms. But it's not what I want. I cannot integrate the product of two holomorphic top forms. So there are actually two reasons why I cannot make it, okay? First reason is that I need to integrate the D, D differential form and not this guy. The second reason is that these holomorphic top forms, the product diverges. So simple example is, I have P1 of X, P2 of X. How can I integrate? It diverges at infinity. So in physics, people say that if you integrate wrong differential form, you have fermionic zero, okay? In physics, people say that you have so-called fermionic zero modes that are not soaked up. I'm sorry. Because when you have Berezin integral, you need to have exactly n thetas. And if you have not enough thetas, the integral is zero, and it's called fermionic zero. So having wrong type of differential form means that you have fermionic zero. Having polynomials that grow at infinity means that you have bosonic infinity. Okay? So the goal is to cancel fermionic zero times bosonic infinity. And you can get something finite. So that's what you teach in the first year calculus course. That zero times infinity could be finite. So this zero, wrong type of the form, and this infinity is divergence. However, there is a universal answer for such problem. It means that what you are doing, you are studying the wrong representative, okay? Because you study holomorphic representative. The idea is to put D bar back, okay? And study proper representative. So representatives that could be integrated. In some sense, you may treat it as a resolvent, okay? I don't know what actually we are resolving, but I'm replacing the complex to something that is quasi-isomorphic to it. And on the cohomology of the quasi-isomorphic complex, we have a pairing, okay? Maybe there are some mathematical terms explaining this. So, I mean pairing in cohomology. So, I never heard that in order to define a pairing in cohomology, we need to go to resolvent. But I'll ask someone. Maybe someone could explain to me. But maybe this is a more general case. So why, when we study pairing with cohomology, we have to go to resolvent? Because without this resolvent, it's not clear what you are doing. So maybe there is a more general construction, more abstract, but I understand it using Dalbo resolvent, okay? And using Dalbo resolvent, it means that we would like to replace dW plus ZD complex by quasi-isomorphic D bar plus dW plus ZD complex. If D bar has no cohomology, so on affine spaces. If the space is not affine, we need to think what to do. So I'm not covering all possibilities. I'm trying to tell you what I think happens. Now, I will say that I'm studying not polynomial of x dx. You see, I say polynomial of x dx, I could say something holomorphic, but I will write it in Kiyosaki terms. You may later rewrite it in general terms. Okay. No, I'll do it myself. But I'll do it in parallel. So here I have omega over f to some power k, I don't know. Just to show that it is something with a pole. And here is the example. Then I should take a homotopy. And this homotopy, I'm looking at another complex, the complex of Schwarz forms, Laurent Schwarz. So here I need to do what? Plus ZD. And here I need to put something. So idea would be to replace one of the differential forms by this. Okay. And here I have this I, P minus Q. and I want this thing to be integrable. And this trick is a well-known Edward Witten trick. And maybe he borrowed it from Mathieu, maybe he invented it himself. I don't actually know, because I was not around these days. But there is this trick. So you write here homotopical 1, because exact something is homotopical 0. So e to the 0 is 1, homotopical 1. You know, I like these formulas, like x to 0 is log, yes. 1 is e to 0. So this is 1 equals e to 0 formula. Now I need to look for something that should stand here. The best thing to put here, so let me see, what can I put here? I would like to take for this star the following thing. I would like to have something like dw norm square plus something else. Okay? Because in this case, this would be integrable. This would be of the Schwarz type. How can I do it? So I know that dw nicely interacts with d bar w bar star. Okay? This commutator seems to be exactly dw norm squared. Okay? Let us see how it works. So dw is actually dw over dxi, dxi. So now let us see. So here is a star, and I also want complex conjugation somewhere. So, yes. So what is dx bar I bar star star? Okay. No complex conjugation. Let us compute this guy. So due to good old Hodge, it is this. I hope, Dong, you understand what do I mean, d over dxj. dxj is just a not variable. I take derivative. So in the 19th century, people write it this, like this. But it's not very transparent. I prefer this. Okay? So when I so that's how I prove this formula. Take the derivative, see that it differentiates dxj, and here we have dxi. That's it. Formula is proven. So I know what to take here. Good old Hodge tells me that I can put here this guy. By the way, here, this W bar is completely conjugated to this W. Because later on, I can put here number 1, and I can put here the D bar W bar 2. Okay? I can do this. You should not mix 1 and 2. So 1 is for localization. 2 is for bicomplex structure. They are different. So I spent some time explaining that W1 bar and W2 bar are different. So when I put it like this, I could also put localization parameter lambda. So lambda stands for localization. So since nothing depends on lambda, I can turn this lambda either to 0 or to infinity, okay? So let me first see, what would I get? In this one-dimensional case, I understand what I have here. But there is another thing here. So I have minus D bar star, D bar W1 bar star, something unusual with lambda, minus lambda norm dW bar, and also Z term, okay? Now let us see. The second term makes it convergent over the X. So here we cure bosonic divergence, okay? This term turns dx into dx bar. Because this term is definitely what? Dx bar, second derivative of W bar, derivative over dx, okay? And here is the Kähler metric somewhere here. So it's exactly what I need. I am killing the wrong fermion, I am putting the right fermion. So this thing cures me the equation of fermionic zero modes. So I had 0, now it's not 0 anymore. I have lambda here, I have lambda here. And you know what? These two lambdas would cancel. So first, let me compute at lambda equal to infinity. Then assume for a moment that W has simple zeros, that dW has simple zeros. It's not a necessary requirement. My claim is that I already computed everything. But if it has simple zeros, I can simplify further. Okay? Because then I can consider quadratic approximation. In this case, I have in the exponential dW over dx. Second, so for So I need to consider the first derivative, dw bar over dx. And that's it. So I need to study quadratic, sorry, I need to study, no, not like that. I need to study quadratic approximation. So here I have dw. Okay, in quadratic approximation, so dw is 0, so I have to study second derivative of w. Second derivative of w bar times xx bar. I have also a odd formula for the odd part. And here I just have this as a multiplier. Second derivative of w bar. And that's it. And I also have these polynomials of x and lambda. And then I'm taking this integral. And what I get here is, of course, p1 of x, p2 of x. And here is, of course, the second derivative, and then summing over the critical points. So do you see what I wrote here? So I can put it upstairs. Okay, so this is the pairing plus z corrections. They're important. These z corrections are important. They are very important. But at the moment, I'm just computing this.
We're saying that to integrate the multiple of these two top forms, you kind of forced to introduce the homotopy operators, right?
Yes.
And this homotopy operator, after you apply this operator, the first term of this integration is a stationary phase approximation of W with respect to P1 times
Yes.
P2.
Yes, the integrand is, the integrand goes like this, yes. Stationary phase. And I may consider the leading term.
Mhm.
And I see how nicely lambdas are cancelled, because I actually have 1 over lambda from bosons, from x's, and lambda from fermions. And this lambda cancel. I have lambda here in denominator. I have lambda in exponential. Sorry, I have lambda here from fermions. Lambda from bosons. Lambda from bosons goes to denominator. Lambda from fermions is a numerator. And it is clear that I have a general formula. And in the general formula, I have determinant of dw over dxxi dxj at xi in local coordinates. And moreover, this formula is invariant because p's are coefficients in front of the top forms. So altogether, you see, extracting coefficient p1 and taking derivative in fixed coordinates are linked together. So if omega 1 is p1 dx1 dxn, omega 2 is p2 dx1 dxn, so I write it in coordinates. Then I have this formula in coordinates. And the answer is independent of the choice of coordinates. If you make change of coordinates, you will have multiplication here, here, and indeterminate. Okay? They cancel. So it is one of the formulas that I have. So this is a pairing. Then you may ask why this pairing is called higher residue. It's a number, it's a formula. It is because there are other ways to write down this pairing. The same pairing, but different formula. So here I used the assumption that W has simple critical points. Now I'll try to work out without this assumption. Okay? So without this assumption, I still need to think, how can I compute this integral? So now I'm again with my favorite integral. E to the minus dw squared. So here I have p1 of x dx. Here I have p2 dx. Here I have this regularization factor. You know what I can do? I can do the following. I know that everything is convergent. So I can cut out from x the place where not w, but dw goes to 0. Okay? So it's d of dw, not of w. So it's not infinity of w. It's a divisor. It's divisor of dw. Okay, please do not mix them. But still, it's a divisor. Okay. Okay, it's not a divisor. It's a manifold where dw goes to 0. So I consider one-dimensional case. So when I cut it, I can do the following thing. I can try to see that this object, so now I transform this dx into dx bar, and I can see, sorry, lambda here, and I can see that all this is a total derivative. Why it's a total derivative? Because this guy is the bar of this, right? But not exactly. I have to divide over dw. So what I do here? I take this piece. And I say that this piece is d bar of what? Of e to the minus lambda norm square of w divided over dw. So this is in one-dimensional case. So to be honest, I need to put here w prime and I need to put here p2 of x dx, and I need to put here p1 of x. Or maybe I need to put it like this. So in one dimension, I can divide. Maybe I can generalize it to higher dimensions. I have never checked. But in one dimension, you can do it like this. Now you can take this d bar out and you get the residue. You may ask, what do I mean when I'm saying residue? I have something non-holomorphic. Yes, I have something non-holomorphic, but residue means that I integrate over a tubular neighborhood of dw equals to 0. Okay? And here this thing goes away. Because this guy in exponential vanishes. That's why I have exactly this formula. So residue means that I integrate over infinitesimally small neighborhood of divisor of dw. So that's how I get this formula. And when people speak about residue pairing, they speak not about this formula, but about that formula. You see, I told you that today I am going to write down formulas, okay? I can say words, I can write down formulas. These formulas, that formulas. What formulas you need, I will write, okay? So it is the formula integral around w bar of x equal to 0. But now, in the simplest case, these integrals could be taken to infinity. This is also origin integral around infinity. So it is the second formula. So I take residue, I have something holomorphic, I go to infinity. Maybe it's a third formula. First formula, second formula, third formula. Okay? How these formulas are related? If you have, if W has critical points, you compute this residue integral, you are here. then it doesn't matter what are the critical points. You have this formula, you just can take a contour deformation. You are here. Now, is it possible to understand why we have integral around infinity here? Could we guess it from the very beginning?
So we are measuring the divergence at infinity? The divisor we cut out at the first place? Is that...
So this contour deformation is a technical argument, okay? It's not a conceptual explanation saying that we have this because of contour deformation. Come on, contour deformation is what you teach people as a calculus second year. Take integral by contour deformation. It's for junior students. We are scientists. We need to understand conceptually what's going on. Here we see that this comes from localization at lambda equal to infinity. So now we need to think a bit. We are scientists, we are thinking, we are not computing. Now let us see. Is it possible to evaluate this integral on the opposite limit when lambda is going to 0? So look, when lambda is going to 0, this thing that is not in the exponent goes to 0 because of this lambda. So it means that we have 0 contribution from the finite piece of the manifold X. Okay? So everything goes to infinity. So we can compensate. Here we are compensating the 0. As I told from the very beginning, we are compensating the 0 by contribution of infinity. That's why we should always say that that we can go to infinity, and that's how it goes. And you may even try to evaluate it this way, because it's what you have at infinity. So in order to evaluate this thing at infinity, you need to extract infinity out of here. So here we have divisor of derivative, and here we have divisor of the function. Okay? That's why these formulas, you see, have some meaning. Okay? It's not just contour, taking contours here or there. And that's why these formulas are important in mathematical physics, not only in singularity theory. So after I explained you these formulas in the Kyoji-Saito theory, okay, let me say something about singularity, about mathematical physics. Look, what does it mean? It means that it means what? That the integral around infinity could be taken to the integral over critical points. So integral around infinity localizes. Okay, now what are these infinities? These infinities are the boundaries in configuration space. So would we properly do these things? We would be able to understand this integral over the infinity in configuration space as an integral over critical points of W. Okay, so actually this leads to so-called scattering equation in string theory, and maybe I'll explain it later. here I just, you see, I do the two-step procedure. First, I tell you what are the interesting questions and phenomena in the subject. And later on, in one talk or in two talks, I'll explain you the subject. Because I cannot explain you something before you find that it is interesting and puzzling. Okay? So this is like a criminal story. If I start to tell you who is the murderer, yes, and explain to you, there would be no point to read the novel. Okay? First, you need to be puzzled, and then I'll give you an answer. All right? So just see that this thing could be this phenomena happens on configuration space. Now, if you consider this integral as an integral over the moduli space of the Riemann surfaces, then the boundary is the field theory limit. So this formula has another has an avatar, okay? Another incarnation, avatar of this formula is that field theory limit of string theory equals to localization as the solutions of the scattering equation of Gross-Mende. That's why this is very important and interesting. But meanwhile, I want to show you some other formula, okay? Today, there will be formulas. I want to tell you the puzzle and solution. So, consider the Landau-Ginzburg theory with superpotential W of one variable, and consider observables P1 of x dx, etc., P4 of x dx. And let us discuss the following thing. Let us discuss the 3-point function and the 4-point function. I mentioned it, but now it's time to write down formulas, okay? 3-point function. So you have this differential form. It corresponds to, so these are forms and these are polyvectors. So polyvectors associated to this form is of course a function, okay? So polyvector here is a function. Now, what is a 3-point function? So you remember this formula in Calabi-Yau case. Now this formula reads as follows: P1, P2, P3, omega. I'm rewriting this because this mu, how this mu happened? I take something from, I take polyvectors out of differential forms. So here I have differential forms, here I have polyvectors. I even put here dx. And now, in the compact case, there was this integral. Now we know what to put here. Okay. So this is a 3-point function. Okay. Now, let me tell you the puzzle and the solution immediately. Okay. Now let us see what is the 4-point function. Naively, I may say that I have point where I have P4, and I take so-called two observable integrate over the sphere. Okay, it's naive point of view. So naively, I need to put here P3, P2, P1, d of w plus t P4, integral d over dt, okay, at t equals 0. Naively, I may think that I need to compute correlator in the deformed background, right? So it should be P3, P2, P1, P4 prime. I'm not afraid of writing simple formulas, you know. This one, integral around infinity. Sorry, I have w prime. I take derivative like this. Okay? So I have it. I can easily take derivative because in this representation, I don't need to look for the critical points. So this is the formula. And then you may look at this formula and see, come on, this formula is not invariant under permutations 1, 2, 3, and 4. Because in string theory, I could consider the point number 3 running, point number 2 running, or point number 1 running. So something is wrong in this formula. So can we correct it? And what is the reason of this correction? So what I understand, that when I'm making this moduli space integral, there are infrared regions when 2 points come together. And there is this ill-defined infrared contributions that has to be replaced by some kind of a contact term. And this contact term could or should depend on W. So actually, it's not a right formula. I need to add here contributions from the contact terms or infrared regions. So CW of P4, P3, P2, P1, plus 2 more terms. And I have to divide it by W prime. So this should be the correct formula. So now I am wise and I understand that it would mean that when W is changing, P's are also changing. So I need to have a connection. So the fact that naive P's are also closed does not mean that it is the right thing to do. So I need to have a connection, not because old representatives are not closed anymore. They are closed, but they are parallelly transported into a stupid connection. in the naive connection. And we know that there should be a proper connection. And by trial and error method, you may check. And that's what I did before I understood all this. That everything is okay if you take CW P1, P2 being equal to P1 times P2 over W prime plus and this is formula that is Kyoji-Saito connection. I just write it in this way because it is not easy to find it in Kyoji-Saito's paper. And instead of putting p's here, he writes derivatives and times, and it produces wrong associations. You know? You may write best formulas, but if you do not explain them properly, nobody would understand what you mean because of wrong intuition. Okay? In particular, if you are writing a text, and if you will call holomorphic coordinates by Greek letters, nobody would be able to read your work. So when you talk about so-called Landau-Ginzburg models or type B models, where observables are polyvector fields, there should be polynomials. You should write formula in terms of polynomials. Okay? When you are talking about 4-point function, you should write it dong. You should write it in a way that is intuitively proper. So let me explain this formula. So here I'm writing simple formulas. So first of all, what is this prime for? You see, everything is for something, right? So this prime actually came from D, and this D was G naught minus. And I told you that under the general ground connection was G naught minus exact. Okay? So here I explain what is going on. It is explanation of this prime. Now, what is explanation of this W prime in the denominator? Of course, 1 over W prime is the attempt to take 1 over Q. So now you may see that it looks like this. 1 over Q of something. And you know why you have to take 1 over Q. It is because when you are taking infrared integral, you have a long cube. You have here something like Hamiltonian. And the integral over the length gives you homotopy. That's why you should be prepared to see this 1 over Q. It's homotopy. Now, here we have a product. It's also a proper thing. Because in the formulas, you were expected to take the product of polyvector fields. Okay? And then apply homotopy to it. So you expect this. instead, you expect this. G naught minus, you have it. Homotopy. This somehow stands for homotopy. And the product. We just need to understand in which sense this plus means homotopy. And this plus means you have the rational function. You expand it, you take a positive part. You expand it at infinity, as far as I remember. Okay? Then what does this mean? So there are two cases. Easy case, easy, as people write in the United States, when P1 times P2 is proportional to W prime. Okay? It means that this product is exact. In this case, you can divide. You don't need to take, you can forget about plus. So you see that plus is related to the case when the product is not exact. Now we understand what the product stands for. We need to take a product of P1, P2. We should take a minus. We should take the representative, I call it sigma, of the class in Q cohomology. And this guy is already exact. Now, why this product? Now, what are these representatives? So, idea is that class of W prime cohomology is represented by span of dx to the power n minus 2. Oh, sorry, x and dx. Lower monomials. These are representatives. These are the good section. So this formula is about the following. If in the product you go outside this range, you need to subtract lower degrees and divide by W prime. But now, this formula could be written as P1, P2 over W prime. Here I have P1, P2 over W prime minus. Minus means lower degree. And this is exactly P1, P2 over W prime plus. Okay? So minus means lower degrees. Here we have plus. And this is the explanation of this formula. And now, when you put it in here with these contact terms, you may check that it is symmetric. Okay? So that's how things are going on in type B theory. By the way, I think I need to show formulas. Okay. Today, the second half of my talk, I'm showing formulas. You see, here is kind of computation. To divide, to take plus part, minus part, to move contours, etc. Yes?
So somehow,
yes.
so this gives this infinity structure because you have the homotopy.
It gives it gives a type of infinity structure, but not a infinity. It
Okay.
gives a higher operation in Frobenius algebra. It gives a 3-to-1 cyclic operation. Okay.
Yes. Okay. Yeah. But if you can consider correlation functions for several polynomials.
Of course, I can do many things. I could go to open case, and then I'll have a infinity.
Yes.
I can study closed case. I can do many things. What I'm trying to explain here is the simplest case where we have non-compact target. So all this was intentional. You see, the intent to study these formulas in such detail is not to reproduce the integrable hierarchy again. The intent is to understand what happens for non-compact B models, okay, in particular, and how to integrate over configuration space in general. Because you may consider, and it's important, you may consider the configuration space as the non-compact complex manifold. And this is something that never came to my mind before I read the recent works of Misera and maybe Shili. I never thought about configuration space as a target space. Because for me, this non-compact Calabi-Yau's, okay, were targets. And now they turn out to be worldsheets. So you see, in Sigma model, there is only one revolution you need to make. So people used that target could be a worldsheet. But
yes.
whenever you see it, you are always surprised. Okay.
Sorry. So you said that how to get an infinity.
It's not A infinity, Sam. It is so-called. It is not even L infinity. It is
Frobenius.
WDVV. It's also infinity structure. It's WDVV.
Okay.
It's also infinity. But it was not called infinity at the moment when it appeared.
Okay. So it's also possible to consider bundles.
You are right. You
Yes.
are absolutely right.
Yes.
And after this story, it is very instructive to consider the open string version.
Yes.
Because it was the closed string version. It's very instructive to consider open string version.
Yes.
And check how closed string things are go together with the open string. Okay. So there should be some constructive so-called open-closed theory for generalized type B model. And here, Sam, you will get your favorite A infinity.
Okay, I see. So from this, one can get, yes, from the bundle, you can take a large n, probably.
So in particular, it's interesting to study corresponding structures.
Okay.
Don't. So it's so you maybe would be interested in this because it is the B version of Fukaya in general case, not only in exponential case like Toda, but in general case. Because Fukaya category leads to very particular B models. Okay. But it is interesting. So it is also interesting to study general B models. Okay.
Yeah. So there are some conjectures.
Not only those B models who are mirrors are interesting. Let me put it this way. There are other B models that are also interesting. Quadratic theory. It is interesting. However, it is not a mirror of anything. It is actually a fake mirror of Vafa. So when Vafa was studying mirror symmetry, he had an idea that mirror to CP1 is Landau-Ginzburg with the cubic superpotential. So later he took this idea back. At least he was unclear, and people were also unclear.
For the bundle case, there are some proposals. So the observers would be given by matrix factorization.
Yes.
By Kontsevich, and also clarified by Kapustin. So
Yes.
there's also some conjecture localization for this open, for this bundle case.
Of course, of course. So, what would be interesting? It would be interesting to study this.
Yes.
Yes, of course. So it would be interesting to see how all this is related to Kyoji-Saito theory.
So I guess.
I mean,
so from Sleeth's work, he can get this higher residue from BV.
Sam, let me say, I
Yes.
got this higher residue pairing in
Yes.
the work of 98. Okay.
Yeah. Yes.
So,
Without it
you
using
see,
BV.
higher residue comes when you do the same thing and you have Z term also. If you have Z term, you have this term. It also comes with lambda.
Yes.
You can compute this derivative and you can see that Z term, here we have P prime divided by something.
Yes. I see.
So actually, you can get this. I can discuss it later on.
I see. Okay.
Okay.
So you got this high residue from localization.
Actually, Sam, I got this high residue in 98. I published it in Kyoji-Saito volume. I put it on the archive.
Yes.
Okay, so it happens that after 20 years, this idea was forgotten. Okay, so Shili independently discovered it. Okay.
Yes.
So I have no objections to Shili.
It's a different method. Yeah. It's
the same method. The same method. Sam, this same method.
Same method.
This method is the same. To take integrable representative. Method the same, pairing the same, formulas the same, everything is the same. I admit that he did it independently, but everything is the same.
I see. But I understood he got this from BV.
You see, it's not from BV. It doesn't matter how you get this pencil of differential.
Okay. I see.
So okay, I got the pencil of differentials from Iguchi. Okay, but
I see.
so but it was clear. Maybe so. Iguchi wrote a paper.
Mhm.
So he called it Loeffler's descendants, and then he was explaining why my descendants are wrong.
Mhm.
However, my descendants are right, and he forgot the contact terms. That's why he told that they are wrong. So he wrote a paper where he discussed this issue.
I see.
And from his paper, from his critics to my paper, I realized that you have to interpret things in terms of the pencil. So this is the easiest way to see.
Mhm.
With G naught minus.
I see.
But okay, so it was 90.
Mhm.
Then I
Yes.
wrote a paper at 98. And if somebody could say that this paper has mistakes, I would like people to see these mistakes. I understand that Shelley was not reading this paper. It's normal.
Yes.
But when I say that there is such a paper,
Mhm.
okay,
So-
at least then it's polite to refer to both of us.
Okay.
Okay.
Sure.
However, I was 20 years earlier.
Yes. And to extend this to the bundle case, is this mathematically, in some sense, is still open, right?
I think it's still open, yes.
Mhm.
Not
Yeah.
only this is still open.
Hmm.
I would say that even the theory of primitive form for the for other manifolds, not for the complex plane to the power n, is not done yet. This is not done yet. So I had no time today to discuss to describe the case CP1 with 2 points cut out. That is Toda. But this theory is for any manifold.
Hmm.
It's very simple. Consider a manifold with non-trivial k, okay?
Hmm.
Where k is, of course, canonical class.
Mhm.
Get rid of this device.
Hmm.
You get a nice theory.
Oh. Okay. So it's kind of
So it's
non-compact.
you see, if you don't have Calabi-Yau, it is kind of instruction. Take
Yes.
a manifold,
Yes.
take a compact manifold. It could be Calabi-Yau manifold or could be not Calabi-Yau manifold. If it's not Calabi-Yau manifold, make a Calabi-Yau manifold out of it.
Yes.
Unfortunately, in this case, you need to have superpotential.
Yes. So you.
So
it's
what
kind
we
of-
call compact manifolds, are special cases of non-compact manifolds where we consider a subsector of functions regular at infinity and such that holomorphic top form could be continued there.
Yes.
So in this point of view, normal complex manifold is non-compact with superpotential. And what we call compact manifolds are very particular cases, some strange subsector.
Mhm.
Okay.
Yes.
So I actually like revolutions. I think that we understand something only if we radically change the point of view on the subject.
I see. So the proper setting would be a final manifold, and delete canonical divisor.
By the way, why Fano manifold?
Maybe a Keller manifold, any Keller manifold.
Any
Well,
Keller manifold.
Not why
And
why
Cauchy
not?
ware, I mentioned, Cauchy ware, considered Riemann surface
Hmm.
of genus G.
Uh-huh.
And of course, he deleted some points. By the way, it's enough to delete one point, because on the Riemann surface, okay, the class of divisors is just just a point. No, 1 point maybe is not enough. Okay, I need to think if it's a point or a set of points because of this Picard problem. In some sense, I think point is enough because you do not need to consider a W. It's enough to consider holomorphic one form.
Okay.
However,
Okay.
you need to deform this holomorphic one form with derivatives of holomorphic functions.
Okay.
But maybe we can see now. I spoke for 3 hours. Typically,
Yes,
we
sure. Yes. Yes. Maybe. Yeah. That's.
But of course, the proper. So the message here is that non-compact manifolds with superpotential is a general case.
Yes.
And when we study the particular case of compact manifolds,
Yes.
it is a pity because you don't see the full theory if you study only this.
Yes. Yes. Okay. Okay. Very good. So maybe we should stop today. And you have spent.
Yes.
You have lecture for 3 hours more, over 3 hours. Okay.
No, I spoke for less than 3 hours because
Oh.
I started. I checked the time.
Okay. Okay.
Okay.
Okay.
Oh,
So-
Dong.
Yes.
So, did you got something interesting today?
Yeah, actually, the last formula you showed us was quite interesting because I well saw the high residue pairing formula, but this is the first time I somehow you understand in the more down to the earth terms. So thank you very much. And
I also could. Okay, so it means that next time
Mhm.
I'll explain you higher residue because with derivatives.
I see, so good. And as a question, I see a very similar formula on the board to the difference the Gauss-Manin connection with spectral parameters.
It's
You
the
might-
same connection.
Yes, the same connection, right? Yeah, but
No,
you-
it's called. Without this, it's Gauss-Manin.
I see. So that's very good. And but I really want to see once again this the mirror the total hierarchies from the mirror potential of P1,
Okay.
of course, not just for me, for
Yes.
That's
So
the
next
second
time, so
time,
next Friday.
yes.
So you see, so here I explained the third part. Okay, I'm sorry.
And also
Because
don't
without
forget
this-
about this, also don't forget about this integrable hierarchies.
Yes. So actually, integrable hierarchies come when you integrate this connection.
Yeah, I really
But-
really want to understand exactly that.
But I still want to explain why this is important. Why higher residue pairing? Where this higher residue pairing? So what is this localization that leads to this higher residue pairing? Why it has two forms?
I see. It's very good, very good. So, by the way, you somehow add this contact terms on the naive 4-point correlation function.
Not me. I somehow understood this. Maybe it was Bloch and Varchenko who interpreted it this way.
I see.
Okay, so several people. Yes, of course.
Mhm. And
Yes, I added contact terms. Yes.
so So, so how can you find this contact term in a more philosophical way? It seems like you get it from
In the more
term.
philosophical way, and that's what I explained in the paper. In the more philosophical way, you are finding them in the following way. You need to study this good section. Okay. So how are you studying this good section? This good section is something about polynomials. So actually you do the following. You study good section in terms of harmonic forms, okay,
Yes.
or kernels of the Laplacian. And then you take the holomorphic piece of it. And the holomorphic piece of the kernel of the Hamiltonian is a good section.
So once again, the kernels of
Okay.
the Laplacians of the Hamiltonians.
Okay, example. Suppose you have W that is x squared, okay? You may easily see that and W1 and W2 bar is x bar squared, okay? Then you can easily see that the kernel of the Hamiltonian is like this. Let me put here T squared. Let me put here T bar squared. T bar, T dx plus T bar dx bar. So this is the kernel of Hamiltonian. Okay? And then what you can do? You can go to the critical point and then you may take x bar to 0. So you may contract with anti-holomorphic field. So from this, you will get T dx. You can see, oh, sorry, x bar. So this is integrable sum.
Yes.
From this, you can get T dx. And this dx is a good section.
Yes, of course.
So you understand how the good section appears. You have the kernel of H, and then you consider x bar going to 0. Then kernel of H becomes the span of good section.
Okay, good. Good.
So this is an answer what good section is. And I prove that such good section satisfies all axioms of Kioji-Saito theory.
I see. I got it. So,
but then how to apply it? In the case of the AN case, good section are lower dimensional polynomial.
Exactly. Okay.
That is the origin of this class. By the way, if you try to see that everything is symmetric in P1, P2, P3 form, it would also involve the invariance of the pairing with respect to this connection.
That's right.
It is a piece of this data. But this comes from the fact that this pairing is actually independent on Z, by the way. I will show it. That ability to have, okay. I will tell it next time. Okay, so here I explained two things today. So I explained this issue of what? Of divergences in mathematical physics and and in the singularity theory. Then I explain the trick, localization, homotopy. And in this localization, I got formulas for pairing, for high residue pairing, in both infrared and ultraviolet form. And of course, next step would be to apply these formulas to Riemann surfaces for the beginning, in particular to CP1 to get Toda, to Riemann surface of genus G to get so-called Krichet-Weber integrable system, and to general manifolds. At least to get the so-called dispersionless version. Okay?
Sounds great. So that would be the next topic.
Yes.
For next Friday. That's very good.
Yes. Okay? So still, you see the second part, I explained something about singularity theory. Like I explained connection and how it's related to the 4-point correlation. Okay?
Right.
Okay.
Okay, should I stop recording?
Yes, please stop. So Sam disappeared, but